The problem statement, which has been taken from GATE Physics 2019 paper, reads as follows. For a given load resistance RL equal to 4.7 ohms, the power transfer efficiency is, which is defined as eta equal to P load over P total of a DC voltage source and a DC current source with internal resistances R1 and R2 respectively are equal. The product R1 R2 in units of ohm square is. This is a numerical answer type problem, and we have been asked to round off our answer to one decimal place. Before we start solving, let's visit some relevant concepts. On the left, we have an ideal voltage source which has internal resistance Rs equal to 0. On the right, we have a practical voltage source which has a non-zero, non-infinite internal resistance Rs. Now, let's apply a load RL to both of these power sources, and let's try to calculate what power is delivered to these sources. Now, here, let's assume a current I1 is flowing through this circuit. Simply applying KVL, we can write that Vs minus I1 RL equal to 0. Now, power delivered to load, let's write it as P load. This will be equal to current flowing through the load, which is I1 square times RL. And the power supplied by the voltage source here, let's call it P supplied. This will be equal to the voltage rating of the voltage source multiplied by the current supplied, which is I1 in this case. The power transfer efficiency eta, which is equal to power supplied to the load over power supplied by the battery. This will be equal to then I1 square RL over Vs I1. I1 gets cancelled and we get I1 RL over Vs. Now, note that in this expression we have Vs equal to I1 RL. We'll substitute this here and we'll get power transfer efficiency of unity. This is the best you can get. This means that all the power that you are supplying, whatever power is being supplied by voltage source Vs, is being delivered to the load RL. Now note that this is an ideal voltage source. In real circuits, we will not encounter this situation. We'll encounter something like this. There will be some parasitic capacitances and resistances will give rise to a resistance of Rs. Now let's try to solve what kind of power efficiencies we get in this case. Again, let's assume that a current I is flowing through this circuit. Again, writing KVL, I can write Vs minus IRS minus IRL equal to 0. Now, this will give me that the current of Vs over Rs plus RL. This is the current flowing through the circuit. Now, again, let's try to write the power delivery efficiencies eta, which is equal to power delivered to the load divided by power supplied by the battery. I'm calling it as PSUPP. Now, power delivered to the load again would be I square, because I is the current flowing through this load, times RL divided by, now power supplied here is the voltage rating of the battery, which is Vs, times the current flowing through the battery, which is again I. So again we'll write Vs into I. Now one I gets cancelled, so we get I RL over Vs. Now we know the value of I from this expression, correct? So let's place this here. So we'll get Vs over Rs plus RL, excuse me, times RL over Vs. Now Vs and Vs gets cancelled and you will get a result RL over Rs plus RL. Now note that since Rs is a positive quantity, RL over Rs plus RL will always be less than unity. And this is a real life scenario, which I'm telling you will never get a power transfer efficiency of 1. Now we'll extend the same principle to current sources. On the left again we have an ideal current source which has an internal resistance of infinity. Effectively no current, all the current will be flowing. We'll see that. On the other hand, in a practical current source we have a shunt internal resistance which is non-zero and non-infinite. Again we'll do the same thing, that we'll assume that this current source is being used to drive a load resistance RL. In both the cases we'll assume that the load resistance is the same. Again, assuming that a current I is flowing through the circuit, we'll write the KVL expressions. The KVL expression would be that V out is equal to IS times RL. Note that I is equal to IS in this case. Since there is no current flowing through this branch, if we apply the KCL at this node, all the current which is being supplied here should go here, and thus we get I equal to IS. Now again, writing the power transfer efficiencies, we'll get power delivered to the load upon power of source. So what do we get? Power delivered to the load we know is I square RL, so which is I square times RL over power provided by source. Now this is interesting. So what is the power provided by source? Power provided by source is the voltage that the current source is seeing. Now what is the current source seeing? Our current source is seeing a voltage of V out. So we'll simply write V out times, what's the current? The current rating is IS. So I'll write IS. Okay, that's all this. Note that I is equal to IS. So I'm using them interchangeably. So one of them will get cancelled since I is equal to IS, and we will get IRL over V out. Note that we wrote this expression V out equal to IS times RL. So I can write IRL over IS RL. Again I is equal to IS. So we'll get a power transfer efficiency of unity, which makes sense since whatever current is being provided by the current source, none of it is going to any internal resistance. All of it is being delivered to the load. Again, this is an ideal life scenario. Practically we'll have some current flowing through here, and we'll try to solve it right now. Again, let's assume that a current I is flowing through the load resistance RL, and let's assume that a current I1 is flowing through this internal resistance RF. Now let's apply KCL at this node. This is the node I am applying KCL. What does the KCL say? That at any given node, all the current that is coming in, the current that is coming in here is IS, should be equal to the current that is going out. Now there are two currents going out. One is going to the internal resistance, which is I1, plus the second current is going through the load resistance, which is I. This is the expression that we get. Now let's again write the power transfer efficiency expression, which is power delivered to the load divided by power supplied by the source. Now what is the power delivered to the load? It is I square. I is the current flowing through a load resistance times the load resistance value, which is RL, divided by P source. Now what will be the P source? P source would be the voltage that the current source is seeing. What's it seeing? It's seeing V out. So we'll simply write V out times IS. IS is the voltage, IS is the current rating, excuse me. Solving this, we'll get I square times RL. Now note that V out is equal to I times RL. If we apply KVL, or we simply apply Ohm's law across this resistor. So V out, I can write I times RL, this is times IS. RL and RL get cancelled, 1 I goes away, I will get I over IS. Now I'm not getting an expression in terms of resistances which we got in the earlier case. So what's happening here? We'll try to solve it. Now I can write the value of I1 as V out over RF. Note that what I am doing is simply I am applying Ohm's law across this resistor, and we already know that I is equal to V out over RL. So I will substitute the value of I and IS from here to in this expression. So I can write I as V out over RL divided by, so IS would be I1 plus I. Okay, what is the value of I1? I1 is V out over RF plus V out over RL. Now if we take an LCM, we'll get RF into RL divided by RL into RF plus RL. So RL and RL get cancelled and we'll get an expression RF over RF plus RL. I'm just writing it here for more that it's visible, so that it's better visible. So it's RF plus RL. This is the expression that we have gotten. Again, note that since RF is a positive quantity, non-zero quantity, this value will always be less than unity, which makes sense, correct? Now we have gathered the information as to what is the power transfer efficiencies of an practical current source and a practical voltage source. Now we'll get back to our problem and try to solve the problem. Now this is the problem which was provided to us. Okay, I should say that RL was given the value of 4.7 ohms. Now let's try to solve this problem. What we were given is that power transfer efficiency for this circuit, let's call it eta 1, and for this circuit let's call it eta 2. We were given that eta 1 was equal to eta 2. Now we know that we just derived that eta 1 came out to be, I'll go back to that expression. Eta 1 we saw that was this. What was eta 1? It's been written here, I am rewriting it. Eta 1 was RL over RS plus RL. This is the eta for this practical voltage source. So let's plug this value here. So that's RL over, what is the source resistance? Source resistance here is R1. So I'll simply write R1 plus RL. Now what was eta 2? Eta 2 was R2 over R2 plus RL. Now the problem statement says eta 1 equal to eta 2. So we'll simply equate them. So this will give us RL upon R1 plus RL equal to R2 over R2 plus RL. Now what do we do? I will simply invert the numerator and denominator. So we'll get R1 plus RL over RL equal to R2 plus RL over R2. Okay, what do we get here? We will get R1 plus RL plus 1. Just split the denominator across these two terms. Similarly, split the denominator across these two terms. We'll get 1 plus RL over R2. This will give us, so 1 and 1 gets cancelled. So we'll get R1 over RL equal to RL over R2. This implies RL square is R1 times R2, or we can say RL equal to, we were required to find the value of R1, R2. So we can say that we don't need this. So we'll simply get R1, R2 equal to RL square. Now the value of RL has been provided in the question itself. It's here, RL equal to 4.7 volts. So the product of R1, R2 will be equal to 4.7 squared. Okay, what is 4.7 squared? I'll just punch into my calculator what is 4.7 square. Excuse me for a second. So this is 22.09. 22.09. And we were required to round it off to one term. Remember that. So when we round it off, it will come out to be 22.1. So the product of R1, R2, which you were required to find, that comes out to be 22.1, which we will simply put in our answer here. That's it. Thank you for listening. Have a good day.